Most integrals are a battle of patience. They're slow, predictable, and ordinary. Formulas like, the Pythagorean theorem, or the equation of a straight line. But hidden among them is a key which turns the ordinary into the extraordinary. A power that bends factorials, trigonometry, and infinity itself to your will. Prepare yourself to be transformed by an integral so powerful that you may just want to keep its identity a secret. You find yourself in math class, and the professor has just put a formidable integral on the board, one which you are tasked to solve in front of the whole class. The integral is the one from 0 to 1 of t to the 4th times 1 minus t to the 7th dt. Pause the video now if you'd like to figure it out. One approach might be to expand the binomial, or perhaps try the integration by parts method. We'll explore both methods just to see how laborious that method or those methods really are. We'll begin with expanding the binomial. One can see and use the binomial theorem here by allowing 1 minus t to the 7th be put into the formula for the expansion, and using Pascal's triangle to find the coefficients of 7 choose k. These will be the coefficients of our binomial expansion, thus we'll get an alternating series in terms of the powers of t. Multiplying this by t to the 4th, we get a long polynomial expression of 11th degree. Polynomials of this type are not that difficult to integrate once you have the expansion. So integrating this expansion from 0 to 1, term by term, and applying the limits of integration, we get the following series of fractions. They sum to 1 over 3,960, the exact value of our integral. Not the most elegant approach. So if one attempts the integration by parts formula, one might approach it in the following way. If we let u be t to the 4th and dv be 1 minus t to the 7th dt, and follow through with the integration by parts formula, one will notice that the first term in the result will just cancel to 0. And thus we get 1/2 from the integral from 0 to 1 of t to the 3rd times 1 minus t to the 8th dt. We notice a reduction in power in one variable and an increase in power in the other. One then attempts to apply integration by parts again. We'll call this integral the integral I47. And notice that it is equal to 1/2 the integral of I38, hinting at a recursive relationship. The integral I38 is then integrated by parts as follows. And as one would suspect, we get another reduction and increase in powers of our integrand. This is good because we're getting a reduction in at least one power, which will simplify our integrand eventually. So now our integral is equal to 1/2 times 1/3 I to 9. And integrating I of 2 9 by parts, in the same way that we did the others, we get the following result. And so I is equal to 1/2 times 1/3 times 1/5 of I 1/10. So we're almost there. Now I of 1/10 is this integral, and by parts, this integrates to the following. But this is not a very difficult integral to evaluate without parts. Thus we get this integral to be equal to, finally, 1/12. So now we can put our final integral together as a product of fractions, 1/2, 1/3, 1/5, 1/11, and 1/12, which is equal to 1 over 3,960, as you would expect. But this pattern has a familiar feel. What does this remind you of? Catching the attention of one of his classmates, this couple begins to look into this mysterious integral that has a mysterious superpower associated with it, allegedly. Introducing the beta function. The beta function is a function of two variables. It is an integral from 0 to 1 of t to the x minus 1 power times 1 minus t to the y minus 1 power dt, where x and y are greater than 0. And one might ask, does this beta function have a closed form solution that allows one to calculate integrals of this type with superpower style? How do we examine the behavior of these kinds of integrals? Where would you start? And what kind of patterns would you notice? Pause the video now if you would like to work it out yourself. One approach here would be to explore what happens as we let x equal 1, 2, 3, and so on, and let the variable y stay free as a variable. So starting with x equals 1, we will increase x step by step, letting y be free. So beta of 1y would be this following integral, which evaluates to 1 over y. b of 2y evaluates to 1 over y times y plus 1. And b of 3y evaluates to 2 over y times y plus 1 times y plus 2. If we continued this, what pattern appears to be emerging here? Does something here feel familiar to you, or something that you've seen before? What does this remind you of? Perhaps this reminds you of n factorial, defined as the number n times n minus 1 times n minus 2 with all those numbers down to 3 times 2 times 1, where n is a natural number. So the beta function is somehow connected to factorials. And for this we need to introduce another integral superhero, one that understands factorials very well. Do you know what I'm talking about? If you guessed the gamma function, you're correct. And the gamma function is defined by this integral from 0 to infinity of x to the n minus 1 power e to the negative x dx. One of its superpowers is its recursive nature. You see, gamma of n is equal to n minus 1 factorial, which makes its recursive relationship gamma of n plus 1 equal to n times gamma of n. Thus, the beta function is related to the gamma function in the following way. The beta function is equal to gamma of x times gamma of y over gamma of x plus y. And thus we can relate the beta function to the factorial notation that many of you are already familiar with. We are now prepared to handle integrals of the type we saw before, with a little prowess, a little superhero power. So returning to our messy integral from before, which was the integral from 0 to 1 of t to the 4th times 1 minus t raised to the 7th power dt, we notice that this is the beta function evaluated at 5, 8. Which is the gamma function of 5 times the gamma function of 8 over the gamma function of 5 plus 8. And in terms of our factorial notation, this makes short work of the calculation necessary to find the answer with superpower flex. Impressive as this is, it's not the end to its superpower and what it can do against a formidable integral. The professor, angry that you handled that integral so well, throws another one your way. The integral from 0 to 1 of the square root of t times 1 minus t dt is no problem for you, because you have the beta function on your side, and with that, access to the gamma function. Play with this integral for a few moments, pause the video now to see if you can figure it out with your newfound superpower. Representing this in terms of its powers of t and 1 minus t, one can conclude that x and y are given to be 3 halves, both. So we need to calculate the beta function of 3 halves comma 3 halves, which is the gamma function of 3 halves squared over the gamma function of 3. But wait, we didn't learn this in our training. What's the gamma function of 3 halves equal to? Take a minute right now and see if you can figure it out. Well, using the recursive nature of our gamma function, we can reduce the gamma of 3 halves down to 1/2 gamma of 1/2, and then squaring it. But that still remains to the gamma of 1/2 to be discovered. And with a nice substitution of x equals t squared, one can reduce the gamma of 1/2 to, well, a familiar integral, a Gaussian integral. And by squaring this Gaussian integral, we can then evaluate this double integral using a change of coordinates into polar form. So if you have never seen this evaluation of the Gaussian integral, we change over to polar coordinates, which gives us the following double integral. The integral in terms of theta is easy to evaluate to 2 pi. And then making a quick substitution for r, we can evaluate that gamma squared of 1/2 is equal to pi. Thus, our integral that the professor threw our way is equal to pi over 8. The professor transforms to Dr. Octonian and has one more thing up his sleeve, a pure sign of evil. The integral from 0 to pi over 2 of sine raised to the 19th power times cosine raised to the 6th power. Pause the video now and see if you can battle this formidable integral. This might be a nightmare for some, but this integral echoes of the beta function. So let's explore it a little deeper to see if we can't draw this integral out of the beta function. And of course, like always, we start with the basic definition of our beta function, this integral from 0 to 1. By letting t equal the sine squared of theta, 1 minus t would be equal to the cosine squared of theta. Our limits of integration would then change to be 0 to pi over 2. And we would get the sine squared theta raised to the x minus 1 times cosine squared theta raised to the y minus 1 times the 2 sine theta cosine theta give us a way of expressing the beta function in terms of this trigonometric integral, which can also be then rewritten in terms of the gamma function, which gives us access to factorials. A very powerful tool, now at our fingertips, can allow us to calculate the exact value of this integral. Pause the video now if you'd like to give it a try. Discovering that x would be equal to 10 and y is equal to 7 halves, x plus y would be equal to 27 halves, and we can apply our gamma function formula to find out what this is equal in terms of the factorial notation. And using the recursive nature of our gamma function to reduce the gamma of 7 halves down, we get this value. And now all we'll have to do is do a little cancellation with our factorials and some evaluation of powers of 2 in order to evaluate this particular integral completely. But most of the heavy lifting here has been done. So putting the integral together, we'll write out the expansion for our factorials just so we can see the things that actually cancel. The factors of the square root of pi will cancel each other out, and we can begin to cancel common factors in the numerator and the denominator. Cleaning this up a little bit, we'll write all our powers of 2 and any leftover factors we have. Collecting our terms of powers of 2, we get 2 to the 16th power over 185,910,725. Or 65,536 over 185,910,725. The exact value of this very evil integral. And that's due to the beta function. Well, I hope you enjoyed this video. Please hit that like, subscribe, and notification bell for more videos. And I'll leave you with an open problem. Find the exact value of this integral from 0 to 1 of x to the 2024 power times 1 minus x to the 2025 power quantity to the 2025 power dx.